Hello everyone, welcome to another Project Eggbites crash course for JC Math. This one will be about permutations and combinations. So as always, I'll go through a small introduction, then go through some of the PNC content, the questions, and then a little summary at the end. So this is what I'll be going through as the content. So we'll start off simple with counting principle and then slowly go on to more difficult and more technical stuff such as permutations with identical objects, circular permutations, and then finally on combinations. And so the first part is counting principle, which as the name says is just about counting. So let x and y be two events that cannot occur simultaneously. So let's say there's like a stage 1 and a stage 2. If x can occur in x different ways and y can occur in y different ways, then the number of ways that x and y can occur is just x plus y. So let's just say Bob can travel from country A to country B by plane or train. There are 3 possible routes by plane, 4 possible routes by train. How many ways can he travel from country A to country B? So of course for this, there will be the first case where he travels by plane, and there's the second case where he travels by train. And so there are 2 different ways and there's 3 and 4 ways within each case respectively. So you just add up the scenarios. Alternatively, there's also the multiply principle. So suppose that E is an event that can be split into 2 independent events, P and Q, in ordered stages. If P can occur in P ways and Q can occur in Q ways, then P and Q can occur in succession in P at Q ways. So we are basically creating scenarios where let's say P1 happens and then there can be a Q1, a Q2, Q3. So basically you have all these different permutations where each specific stage is very specific and they depend on each other for a specific outcome of the 2 things. So let's say May is interested in buying some potted flowers. The florist store sells 3 pots in 3 colors, brown, yellow, and green. The store also sells 4 types of flowers: rose, tulip, sunflower, and orchid. So if Mary wants to choose 1 flower and 1 pot, how many choices will she have? So there are 3 color possibilities and there are 4 flower possibilities. So in this case, there can be a rose in a brown pot, a sunflower in a yellow pot, or a rose in a green pot. So you can mix all these possibilities together. It's just 3 times 4 to create 12. So this is another question that I see which is rather interesting. It's about Morse code. So Morse code is used to denote digits from 0 to 9 using a string of 5 characters as shown below, either a dot or a dash. So someone wants to create a 0 in a Morse code but forgotten how to do so. So let's say we don't see the 1 to 9 to 0 and it's just a guess between a dot and a dash with 5 characters. So how many possible strings of 5 characters can he even form? So in this case, you either have a dot or dash for the first character, second character, third, fourth, and fifth character is also going to be either a dot or dash. So in this case, there's 2 scenarios, but taking place 5 times. So because there are 2 choices at the 5 checkpoints, the total number of characters is just 2 times 2 times 2 times 2 times 2 to create 32 ways. The next part will be about permutations of distinct objects. So an example is how many possible arrangements are there of the letters A, B, and C together. So there are 2 methods. The first one is that you just list out the arrangements, which is a correct method in itself, and you can do it. So in this case, you have ABC, ACB, BAC, BCA, CAB, and CBA. The problem is that for later questions, you will see that the number of arrangements can be a lot bigger. And so what I recommend is that if you estimate that the number of arrangements available is less than 30, you can try and list out the arrangements. I think a better method, especially for those with a lot more arrangements, is to think of one arrangement of letters ABC as an operator. You fill up 3 boxes. This operation can be carried out in 3 stages. So stage 1 is just thinking of how many ways you can fill the first box, A, B, or C. Second stage will be the second box, which are the remaining 2 letters. And then lastly, we have to think of the last box. And of course, the first 2 letters are already used, so there's only 1 way. So 3 times 2 times 1 will be equal to, 3 factorial equal to 6. The exclamation mark and the equal sign created that automatically. So another example is that a tennis club has n male players and n female players. For a tournament, the players are to be arranged in pairs with each pair consisting of one male and one female. So find the number of possible pairings. So for this question, what the solution did is that they try and take the perspective of just the female choosing the male players. So in the end, the answer was n factorial. Because if you let each female player choose the male partner, the first female player has n choices. The second female player has n minus 1 choices, and so on and so forth until the last female player has only one choice. Because there's an equal number of male and female players. And so it's just packing amongst each other. So, and we are going to do multiplication because each scenario is dependent on the next person. So in this case, the number of ways will be n times n minus 1 times n minus 2 times all the way to 1, which is basically n factorial. So another way they can test the permutation of distinct objects is in the case of fixing certain things together or fixing something in a strict position. So one question is, how many ways are there of arranging the letters of the word society if part 1, the arrangement starts and ends with a vowel, and the second part is the first letter is a consonant and the last letter is a vowel. So if we look at the first part first, arrangement start and end with a vowel. So for all these kind of questions with letters in it, we try and break down into what is a consonant and what is a vowel. So of course the vowels are all A, E, I, O, U. And so in this question, the word society has 3 vowels, O, I, E. So the first slot, or like the first letter that will be arranged, there will be 3 possibilities. Then your last letter will have 2 possibilities. Meanwhile, the 5 other letters in between can take any position between themselves. So it will be, let's say, that first letter in the sandwich will have 5 choices. Next one, 4, next 3, next 2, next 1. So that's why there's 5 factorial possibilities in between the first and the last letter. So in this case, the total number of ways required will be just 3 times 2 times 5 factorial, which will be equal to 720 ways. Then the second part, the first letter is a consonant and the last letter is a vowel. So in this case, there are 4 different consonants. All of them are distinct from each other. So if that's the case, we can fill the second box with the other 5 letters, and they can take any of these positions again. But the first letter has 4 choices. The last letter has 3 choices. The remaining can just swap in between. So in this case, the total number of ways is 4 times 3 times 5 factorial. Then another question. A girl wishes to phone a friend, but cannot remember the exact number. She knows that it is a 5-digit number that is even, and that it consists of digits 2, 3, 4, 5, 6 in some order. And so using this information, find the greatest number of wrong telephone numbers she could try. So this question, there is a slight twist at the end. So you first have to find the number of telephone numbers she can try. And then, of course, because there is one correct number among this giant bunch of numbers, you have to minus 1 at the end. So, step by step first, consider the restriction on the last digit, since the last number must be even. This means the last digit can only be 2, 4, or 6. So there are 3 choices. Then after choosing the last digit, you can arrange the 4 remaining digits without restrictions. This will be 4 factorial because the first letter has 4 choices, second letter 3, third letter 2, last letter 1. So 4 times 3 times 2 times 1, 4 factorial. And so the total number of 5-digit even numbers will just be 3 times 4 factorial, which is 72. But since one of the possibilities will be a correct number, this means there will be 72 minus 1 equals 71 different possibilities. Then this is another scenario for permutation questions, which is grouping objects together. So let's say there are different kinds of books like mathematics, chemistry, history, and geography book. So in this question, how many ways can a librarian arrange all those books on a shelf if all the chemistry books must be together? So whenever they ask you to group objects together, they try and consider all those objects as one unit. So for this case, 3 chemistry books will just be 1 unit. Then you couple that with the 4 math book, the 2 history book, and the 1 geography book. There are so-called 8 units in total. And so the first part will just be arranging all those 8 units. So after you arrange everything, all the chem plus the different math and different history and different geography books are arranged. you then need to arrange the chemistry books within themselves. So when you arrange them within themselves, there's ultimately 3 times 2 times 1 choices, which is 1 3 factorial. And so therefore, the total number of ways will be 8 factorial for the first stage, times 3 factorial for the second stage, which leads to that number, which is 214,920 arrangements. So this is another question. How many ways can a librarian arrange the 4 different mathematics books, 3 different chemistry books, 2 different history books, and 1 geography book? If all books of the same discipline must be together. So unlike the previous question, where we have 8 units, now we group all the subjects into their own respective subjects. So you have math, chemistry, history, and geography. This means there are 4 units or like 4 groups. So after that, when we arrange the 4 groups by 4 factorial, you then need to sort out how you arrange the chemistry books, 3 factorial, how you arrange the 4 math books, so 4 factorial, 2 history books, 2 factorial, and then we also can multiply by the 1 geography book, but the 1 geography book, it arranges itself, so you don't necessarily need to multiply by 1. At the end, the total number of ways to arrange these books is 4 factorial times 3 factorial times 4 factorial times 2 factorial, which is 6,912. And so for these questions, just try and think of them as grouping things into certain units. You arrange the units, and then after you do that, you try and do the arrangements within each unit to get the answer. Then the next one is a slotting method. So basically what a slotting method is that you arrange something first. Then for the thing that you want in a specific position, you put it in the second stage. So in this question, find a number of ways the word combined can be arranged if all the consonants are separated. So again, for all these word-related questions, we try and split first into the consonants and then the vowels. So stage 1 is we find a way to arrange the vowels. We don't want to do the consonants first because we want them to be separated. We just arrange the vowels first. And so after we arrange the vowels, we try and slot it in between each vowel. So think of that as like 3 separate pillars, and there are 4 gaps in between. And so these 4 consonants can be slotted at the positions of the 4 gaps in between. And so when you do that, you arrange the 4 consonants, there will be 4 factorial. So the answer will be 3 factorial times 4 factorial equal 144 different ways. Then another method is the complement method. Basically, what it's saying is that how we want to find a certain specific scenario is that we will consider all the possibilities, and then we will find a very strict but very normal scenario, which basically is the opposite of what we are finding. But because A plus B, let's say, equals the total number of arrangements, and our answer is A, but A is too complicated to find, but B is simple to find. If we just let A equal total number of scenarios minus our B, we can then get the answer. So in this question, find the number of ways 5 men and 2 women can be arranged in a row such that in part 1, 2 women are together, and part 2, 2 women are separated. So for part 1, let's just consider the 2 women are together. So it's similar to our previous part, which is the grouping method. We consider the 2 women as 1 unit. So the first stage, we will arrange the 5 men and 1 unit of women under 6 units, 6 factorial. Stage 2 is the number of ways to arrange the 2 women within that particular unit, so 2 factorial. And so the total number of ways will be 6 factorial times 2 factorial equal 1440. Now the thing is that you can now use this to solve your part 2, because in the first part you already know when the women are together. And of course, when women are separated, it's the opposite of 2 women are together. So we can use the complement method, where basically we find the number of ways to arrange 7 people without restrictions minus the number of ways to arrange 7 people with 2 women together. So the answer in this case will just be 7 factorial. We arrange all the 7 people minus your answer in part 1, which is 1440, which will lead to 3600. So this is the next part, permutations with identical objects. So the number of permutations of n objects taken all at a time reward replacement is given by n factorial divided by n1 factorial and 2 factorial, where n1 is the first type, n2 is the second type, and nk is the kth type. So it is a bit messy, but the example will help this better. So how many ways can the letters in the word bean be arranged? So in this case, there's one B, there's two E's, and there's one N. So because of the repeat E, you can actually eliminate some scenarios. So how we do this is that we will have 4 factorial divided by 1 factorial times 1 factorial times 2 factorial. So any duplicates, you just put the number at the denominator and then you will find the exact number of arrangements. Your 4 factorial stays at the numerator, but in the denominator, you just put the number down there. So in the case of 2e's, you have 2 factorial down there. So then now is on to circular permutations. Note that in, let's say, a usual row, there's an idea of a first position and a last position. So for example, the arrangements ACB, BAC, CBA are different. However, in a circle, there's not necessarily a first or last position to consider, as long as the seats are not numbered. Because two circular arrangements can be considered identical if we just rotate that circle by, let's say, 60 degrees or 120 degrees or 180 degrees. And so, as a result of rotating, you can end up getting these duplicate positions. Now, how we get rid of this duplicate situation is that we try and take reference from one point. We use one object as a reference point, and then we arrange the remaining n-1 objects relative to the fixed object. And so, mathematically, this means that we take n factorial divided by n because we are fixing that position. And so, for all circular permutation questions, the number of permutations of n distinct objects in a circle is given by n minus 1 factorial. So, the example is how many ways can 8 people be seated at a round table? And then this is our second part. How many possible arrangements would there be if the seats are numbered? So the difference between the second part of the question is that the first part, the seats are not unique. But when you go to the second part, the seats are unique. And so in that case, you don't necessarily need to have circular permutations. The first part, how many possible arrangements? You just use the formula I mentioned earlier. 8 minus 1 factorial, 7 factorial, equal 5040. But let's say the seats are numbered, then you can create basically 8 times more unique spots. So in the end, you multiply by the 8 again. And so, when the seats are numbered, we can just multiply by the number of seats. Another question is, in how many ways can 5 men and 5 women be seated at a round table if, in part 1, there are no restrictions, part 2, if no 2 women are seated together, and part 3, if 2 particular women are always seated together. So for part 1, the number of ways is just 10 minus 1 factorial, which is 9 factorial, which will be 362880. Stage 2, part 2, you do the first stage first. So we don't want any women to be seated together. We arrange the males first. 5 minus 1 factorial around the circle is 4 factorial. Stage 2, we seat the woman in the 5 slots between the males. And so there will be another 5 factorial. And so in this case, the number of ways is just 4 factorial times 5 factorial, which is 2880. Then in part 3, we want 2 women to always be seated together, and these 2 women are particular. So for this part, we try and group the 2 particular women as 1 unit, plus the 3 remaining women and the 5 men. So there will be 9 units in total. We arrange the 9 units, so we get 8 factorial. Stage 2 is we seat the 2 particular women, so 2 factorial. So in this case, the number of ways is just 8 factorial times 2 factorial, which will be 80,640. The next part will be about permutations of objects taken from a set of distinct objects with replacement. So the question here is, how many 3-digit numbers can be formed from the set 1, 2, 3, 4, 5, 6 if each of the number contains 3 different digits? And part 2 is if the digits can be replaced. So the difference here is that after each number we select, we then get fewer choices in part 1. But in part 2, there will always be the same number of choices available. So for part 1, the number of ways is that we find a way to choose three numbers among the 6 digits. So first will be 6 choose 3. That's the number of combination of numbers we have. But then we want to see how we can arrange these digits. So the 6 choose 3 is just the different number of permutations. But when we look at the arrangement specifically, then we need to decide how do we want to arrange these numbers among themselves. So among the 3 numbers, the first digit we choose among the 3. Then afterwards we have 2 choices, then 1 choices. So like that, we have 6 choose 3 times 3 times 2 times 1, which is 120 arrangements. Then for part 2, because the digits are repeated, our first digit has 6 choices. Our second digit will have 6 choices as well. And our last digit will have 6 choices as well. And so in this case, the answer is just 6 times 6 times 6, which is 6 power 3 equals 216. Then the next part, which is similar to what I just mentioned previously, is what is combinations. A combination is a selection of objects from a given set, where the order of selection does not matter. So for instance, when we choose a committee of 5 people from a group of 10 people, the order in which the 5 people are selected is not important. But let's say the number of combinations of n distinct objects taken r at a time without replacement, or simply the number of ways to select r objects from n distinct objects. That is basically given by n factorial over r factorial times n minus r factorial, which is basically what you see in your binomial expression, if you remember that from your MS26. So find the number of ways in which 10 people can be divided into 2 groups consisting of 7 and 3 people. So since there are 10 people in total, if you were to choose 7 people from a group, the remaining 3 will automatically form the second group. We are not looking at the specific arrangement. We are not lining up the first and the second group such that, oh, the first 7 people, we arrange them in their specific order, first to second to 7 person. This just wants to choose who goes into the 7, who goes into the 3. So we only need to find a number of ways to choose a group of 7 people. So the number of ways in which 10 people can be divided is basically 10 through 7. Or in other words, 10 factorial over 7 factorial times 3 factorial. So in an examination, candidates have to answer any 7 out of 10 questions. Calculate the number of ways if she selects both the first and the second question, and part 2 if she selects at least one of the 2 questions. So since the first 2 questions are chosen in part 1, the remaining 7, you can select 5 out of the 8 remaining questions. So in this case, it's just 8 choose 5, so 56. And in part 2, we can actually do a complementary set. So we find none of the first 2 questions. So the answer will be the number of ways is all possibilities minus this complementary set we made. So it will just be 10 to 7, and then we minus the scenario where the first 2 questions are chosen. Oh wait, no. No, minus the scenario where none of the first 2 questions are chosen. Because there are 3 ways you can look at it. 1, none of the first 2 questions are chosen. 2, one of the 2 questions are chosen. Number 3, both 2 questions are chosen. So you just minus this one specific scenario, which is just 8 through 7, and then you can get your 1, 1, 2. So now we'll go on to the questions, and there are some scenarios that tend to occur again and again. So like I showed in my examples, there are letter arrangement questions. Then they are creating a code using number digit. Then there's the circular arrangement. Then there will be questions where you try and assemble a team or group of objects. And then the last scenario will be about like color balls, marbles, tokens, cards, basically any item that can be identified, whether it's through a number or color. So the first question is, how many ways can letters of the word nonetheless be arranged in a row if, part 1, the first letter is here E, part 2, all the E's are together, part 3, all the 3 E's are separate. Actually, you realize that after you do part 1, you can kind of do part 2 and part 3 also. Actually, part 2 and part 3 are in a way opposite of each other. So for part 1 first, we try and break down all the letters first. So there are 3 E's, 2 S, 2 N, 1 O. one T, one H, and one L, leading to overall of 11 letters. So the number of letters without restriction is just 11 vector. We can just leave it there first. So to find the number of arrangements, if the first letter is an E, we fix the E first, and then we have 10 remaining letters. So we want to arrange these 10 remaining letters among themselves. And so after we fix the E, there's still 2 E's, 2 S, and 2 N. And so because there are these repeated objects, you have to divide it by 2 factorial, 2 factorial, 2 factorial. So that will lead you to 4, 5, 3, 6, 0, 0 arrangements. And part 2, all the E's are together. So in this case, you can group all the 3 E's as one object, or like one unit. Then you still have the duplicate of S and N. So in this case, instead of 3 E's, you just have one unit. So that's why instead of 11 factorial, it becomes 9 factorial. Then you just divide by the 2 factorial, 2 factorial for the 2S and the 2N. We don't need to deal with the E's because we already grouped them together in the first part. Then the last part is where all 3 E's are separate. So for this question, we try to arrange the remaining letters first. So we arrange the N, O, N, T, H, L, S, S. Then next, we choose 3 slots to place the 3 of the 9. We choose 3 slots to place 3 E's among the 9 slots. So the number of arrangement will be 81 divided by 2 factorial, divided by 2 factorial. Then afterwards we do a 9 choose 3. So we choose where we put the E's. And because all the 3's together does not mean complement. No. Okay, the key thing to take note is that all 3 together does not complement all 3 separate. Because there can be combinations of 2 E's together plus 1 E, and then 1 E plus 2 E's together. Yeah. Next. So 11 cards, each bear a single letter, and can be made to spell the word examination. 3 cards are selected from the 11 cards, and the order of the selection is random. Find how many possible selections can be made if 3 cards all bear different letters. If 2 of the 3 cards bear the same letter, if 2 cards bearing the letter N have been taken away, and find the number of different arrangements for the remaining cards they can be made if no 2 adjacent letters are the same. So for part 1, we try and break it down again. How many unique letters do we have? And so in this case, we have 8 unique letters. So to choose among 3, it's just 8 choose 3 equals 56. For part 2, we want to see if 2 of the 3 cards bear the same letter. So you try and see first what letters are duplicates. So in this case, you have 2 A's, 2 I's, and 2 N's. So choose 3 choose among 1, and then 7 remaining letters you choose 1. So the first part can choose either to have 2 A's, 2 I's, or 2 N's. Then afterwards, we can just choose among the 8 different letters just one of them. So that's why it's 3 choose 1 times 7 choose 1 equal 21. Part 3 is that if 2 cards bearing the same letter N have been taken away, find the number of remaining cards that can be made with no 2 adjacent letters being the same. So to solve this, we just take all the possibilities and then we minus all the scenarios where there are no A's together, there are no I's together, and then you also have to take in this specific combination of all A's and all I's are together. So in this case, it will be 9 factorial divided by 2 factorial divided by 2 factorial. This part is because we remove the 2 N's. So instead of 11 letters, we only have 9. Then we still have the 2 duplicate A's and the 2 duplicate I's. So that first part is why we get 9 factorial over 2 factorial 2 factorial. Then we will minus the possibility where all the A's are together and all the I's are together, which is actually the same number, which is why I multiply by 2. So we minus 2 of 6 factorial times 7 choose 2. Because for this case, when the A's are together, we can just arrange the the 6 remaining letters, and then you just multiply by 7, choose 2 to see where we want to put the A's, the double A's or the double I's inside. And then lastly, it's just minus 7 factorial, where you have all the A's as 1 unit, all the I's as 1 unit, and then after that, you have 7 units in total, 7 factorial to arrange it among themselves. That's how you get the last part. So you take all the possibilities, minus the scenarios, and then you will get 55440. The second scenario is creating a code using number digits. So a 10-digit number is formed by writing down the digits 0 to 9 in some order. No number is allowed to start with 0, and so find how many such numbers are odd and how many numbers are less than 2.5 million. Yeah. So for the first part, we want to see how many numbers are odd. So in this case, we only have to worry about the last digit. In this case, the last digit can either be a 1, a 3, a 5, a 7, or a 9. And so there are 5 options. These 5 options will not multiply by 9 factorial because we are arranging the 9 remaining numbers. But also, we minus 8 factorial. No. Yeah, we minus 8 factorial because it cannot start with 0. And so, it's not going to be 8 factorial because we are not arranging 8 numbers. We still are arranging all 9 numbers. It's just that we are taking into account that strictly, we are minusing the scenario and the first number is a 0, the last digit is a 5, and then we are rearranging the 8 in between. So this 8 factorial times 5 cannot be included. Then for part 2, there are 2 cases. It starts with a 1. So 1 times 9 factorial equal 9 factorial, because then if the first number is 1, any of the 9 digits can arrange among themselves. But in the second scenario, when it starts with a 2, the second digit has to be less than a 5, and then only afterwards you can arrange the 8 numbers among themselves. So in this case, it will be 1 for the 2 times 4, because the second digit has to be less than 5, so 0, 1, 2, 3? No, 1, 2, 3, 4. And then afterwards, 8 factorial equals to 161280. Again, the exclamation mark and the equal sign mess up in my typing, so yeah. So, and then you add these 2 scenarios together, you will get 524160. Next question is how many integers can between 3000 and 5000 be formed using only the digits 1, 2, 3, 4, 5. If part 1, no digits can be repeated, and part 2, the digits can be repeated. Part 3, no repetition of digits is allowed, and the integers form must be something. Okay. We solve part 1 first. So, in the case where no digit will be repeated, we have to look at the first part, which is between 3000 and 5000. So in this case, the number can only be a 3 or 4, which is why we have 2 choices for the first digit. The second choice, we have 4, because we originally had 5 digits, now we only have 4. Then times 3 times 2. So in this case, the total number of integers that can be formed is 2 times 4 times 3 times 2 equals 48. Step 2, again, the first digit has to be either a 3 or 4, but then afterwards, for the second, third, fourth, fifth digit, we can choose any 5 numbers. So the total number of integers can be formed is 2 times 5 times 5 times 5, which is equal to 250. Then the last part, case 1 is that the last digit is 2. Then case, oh, okay. How many integers can be formed given that it's an even number? So to make it an even number, we have 2 scenarios. The last digit is either 2 or the last digit is 4. So, for case 1, the last digit is 2. We still have 2 choices for the first digit, it can be 3 or 4. And then afterwards, we can have a 3, have 3 choices for the second digit, then 2 choices for the third digit. Because bear in mind, our 2 will be fixed as the last digit. So that's why we have lesser numbers. Then, no, yeah. So for that, if the last digit is 2, the number of integers formed is 2 times 3 times 2 equals 12. And for the second case where the last digit is 4, because our number can only be between 3000 and 5000, we have to use 4 as the last number. That means the only first digit we have is a 3. Then afterwards, For a second digit, we can have a 1, a 2, or a 5. Then afterwards, you take 3 minus 1, 2 scenarios. So in this case, the number of integers can be formed is 1 times 3 times 2 equals 6. And so the total number of integers can be formed is an addition of the two cases, which is 12 plus 6 equals 18. Then now to circular arrangement questions. So 8 balls are arranged to form a circle. 3 balls are red, 2 balls are blue, 2 are yellow, and 1 green. The balls are identical except for their colors. So part 1. Find the number of possible arrangements if all 3 red balls are separated from each other. Part 2. Find the number of arrangements if 2 blue balls are separated and 2 yellow are separated. And then part 3. If they are arranged in a row, find the probability that balls of the same color are together. So for part 1, we just want to see the scenario where all 3 red balls are separated from each other. So in this case, we ignore the red balls first. We have 5 blue, yellow, green balls in total. So, and because we are arranging a circle, we just pivot one of the balls. It can be any balls. Because even after we do the 5 minus 5 factorial, we are still dividing by 2 factorial, 2 factorial to account for the duplicates. So this duplication scenario, you can always divide by 2 factorial, 2 factorial for any question. So in this case, the number always should be 6. Then afterwards, we can choose among the 5 gaps in between the 5 balls where we want to place the 3 red balls to make sure they are separated. So in this case, the number of ways will just be 6 times 5 choose 3, which is 60. Part 2. Find the number of arrangements if 2 blue balls are separated and 2 yellow are separated. So in this case, we want 2 things to be separated at the same time. So first off, we try and take a complement. So similar to one of the previous example, we're going to take all the possible ways, minus the way where 2 blue balls are together, 2 yellow balls are together, and then the scenario where both of them are together. So the number of ways without restriction is 8 minus 1 factorial divided by the 3 factorial, 2 factorial, 2 factorial because we have those duplicates. Then the number of ways to arrange the 2 blue balls separated and 2 yellow balls together, or the other scenario is 2 yellow balls are separated and 2 blue balls are together. It's just going to be 5 minus 1 factorial divided by the 3 factorial times 5 choose 2, which is equal to 40. Then the number of ways to arrange if the 2 blue balls are together and the 2 yellow balls are together is going to be 6 minus 1 divided by 3 factorial, which is just 20. So in this case, the number of ways is just your original 210 minus 2 of the 40 minus 20, which will lead to 110. And part 3. If they are arranged in a row, find the probability that balls of the same color are together. So again, this isn't really a circular arrangement question, but basically, you just first find the number of ways without restriction. It will be 8 factorial over 3 factorial, 2 factorial, 2 factorial, which is 1682. And the final probability is that you take 4 factorial, divide by your 1680, which is just going to be 1 over 70. So why we do 4 factorial? It's because we just group all the red balls as 1 unit, group all the blue balls as 1 unit, group all the yellow balls as 1 unit, and then group all the green balls as 1 unit, so you have 4 units in total. 4 factorial arrange it themselves. And the next question. So there are 4 boys and 3 girls. Due to safe management measures, they split themselves into 2 round tables, one with 4 seats and another with 3 seats. Find the number of arrangements such that at each seat table, 2 boys are seated next to each other. So there are several stages to this. The first stage is that you choose 2 boys for each table. So 4 boys choose 2. Then, because when you choose 2 boys for each table, when you choose 2 boys for the first table, the second table will have the remaining 2. Then next, for stage 2, we choose 2 girls for the 4-seater table. So 3 choose 2, then subsequently the other girl will be in the other table. So stage 3.1 is you find the number of arrangements in the 4-seater table. 3 minus 1 factorial times 2 factorial. Then stage 3.2 is that you find the number of arrangements in the 3-seater table. So in this case, it's just 2 minus 1 factorial times 2 factorial. And so in total, the number of arrangements is just going to be 4 choose 2, times 3 choose 2 times 3 minus 1 factorial times 2 factorial times 2 minus 1 factorial times 2 factorial should lead to 144 possibilities. Next part is that at a table, 10 people are directed to a round table with 12 chairs. So find the number of ways to seat the 10 people. So in this case, you have the 12 chairs, you minus 1. So when you pivot 1 chair as the fixed position. Then afterwards, you will factorial it to see where you want to put it. Then you divide by 2 factorial, because in it, we're going to have 2 empty seats. So the thing with people is that each person will be considered as a unique object. Then the 2 empty chairs are considered identical. So that is why we don't need to divide by 10 factorial. We just take the 12 minus 1 factorial to arrange the chairs. Then you divide by 2 factorial to account for the 2 duplicate chairs. Next part is about assembling a team or group of objects. So let's say a group of diplomats is to be chosen to represent 3 islands, K, L, and M. The group is to consist of 8 diplomats and is chosen from the set of 12 diplomats consisting of 3 from K, 4 from L, and 5 from M. Find the number of ways in which the group can be chosen. If it includes in part 1, 2 diplomats from K, 3 from L, and 3 from M. Then part 2 is diplomats from L and M only. Then for part 3, there's at least 4 diplomats from N, and part 4 is there's a diplomat from each island. So part 1, they just want 2 diplomats from K, 3 from L, 3 from M. So this is a very specific scenario. You just take your 3 from K, choose 2, 4 from L, choose 3, 5 from M, choose 3. You get 120. Then the diplomats are from L and M. So in this case, if it's from L and M, you can exclude the 3K people. So 12 diplomats minus the 3K, you just have 9, and then you choose 8. So it's just 9 choose 8 equal 9. So simply you just don't include them in your calculation. Then I never forget to put part 3. We forgot to put part 3. Okay, never mind. Just do part 4. So part 4, they want to create a scenario where there's a diplomat from each island. Is part 3 somewhere above? No, I just forgot part 3. So, okay, you can ignore that. Part 4, find the number of ways if there's a diplomat from each island. So, for this case, we again try to use the complement method. So with the complement method, we try to take no restriction, minus the scenario where there's no K, there's no L, and there's no M. So it's just gonna be 12 choose 8, so 12 choose 8 diplomats. Minus the scenario where there's no K. So if there's no K, you just do 9 choose 8, similar to your part 2 answer. Case 2 is there's no L. So if there's no L, actually just 8 people. So it's just 8 choose 8. Then there's no scenario where there's no M. Because once you remove the 5 people from the group of 12, you just have 7 people. 7 people to fill up 8 diplomats just doesn't work. So you take your 12 choose 8 minus your 9 choose 8 minus your 8 choose 8, it will be 4, 8, 5. Now, you cannot do double counting. Or what I mean is that you cannot do 3 choose 1 times 4 choose 1 times 5 choose 1 times 9 choose 5. It doesn't work. You're going to end up double counting, as let's say your first person in K can also appear in the 3 choose 1 and the 9 choose 5. And so, how this 9 choose 5 comes about is that you're trying to choose the remaining 9 people, let's say. So you first choose your K, your L, your M, then afterwards you just choose the remaining 9. That unfortunately doesn't work, because when you have your 4 choose 1 and your 5 choose 1, then there will be a double counting. So that's why you cannot do that. The best is just do a complement method. Then next question is, a manager originally has 3 goalkeepers, 8 defenders, 4 midfielders, and 5 attackers. He then decides that one of the midfielders can play either a midfielder or defender. So find the number of possible teams. So in this case, we have 3 scenarios here. The first case is the midfielder plays midfield. The second scenario is that the midfielder plays defender. Or third case scenario is that he just doesn't play at all. So if that's the case, the first case, it's just going to be 3 choose 1 for the goalkeepers, 8 choose 4 for the defenders, 3 choose 1 for the midfielders, and then 5 choose 4 for the attackers. So I think it out. But basically, the team, there will be 1 goalkeeper, 4 defender, 2 midfielder, and 4 attacker. So basically, when you have the midfielder, we just fix that midfielder already into the team. So that's why for the first scenario, you have 3,150 players, or like 3,150 scenarios. Second case is when the midfield plays defender. So we can have 4 defenders in a team, but now that we fix this guy as a defender, the number of defenders we can choose is just going to be 8 choose 3. Coupled with the 3 choose 1 goalkeepers, and the 3 choose 2 midfielders, and the 5 choose 4 attackers, we get 2,510 scenarios. Then case 3 is just he doesn't play at all. So you have 3 choose 1 goalkeepers, 8 choose 4 defenders, 3 choose 2 midfielders, 5 choose 4 attackers, you get 3,110. So the total will just be the summation of those 3 cases, it will be 8820. And onto the last scenario, which is just like different color objects. So a box contains 7 beads, 3 red, 2 black, 1 white, and 1 green. In how many ways can 3 beads be chosen and arranged in a row? So again, there are several different scenarios for this kind of question. Just try and pick out the different possible scenarios. See what scenarios and how many arrangements there are in each of them, and you can just add them up together. So the first scenario is 3 same color. The second scenario is 2 same color, and the third scenario is just 3 different colors. So if we have 3 same color, there's only one choice, which is just 3 red balls, 3 red beads. So that's one way. If there's 2 same color, our first stage is that we choose whether you want 2 black or 2 red balls. Then afterwards, we will have a 3 choose 1 for the remaining color. Then we want to arrange it. So when we arrange it in a row, we need to take account that we have 2 duplicates. So in that case, it will be 3 factorial divided by your 2 factorial. So in total, you have 18 ways. Then if there's 3 different colors, it's just going to be a case of 4 choose the 4 colors. You choose 3 of them. Then times 3 factorial to arrange those 3 unique colors, 24. So the sum will just be 1 plus 18 plus 24 is 43. Then, do this question already? This question already. Yeah? No, this is a different RVH question. Okay. So 8 balls are arranged to form a circle. Oh, no, we did this question already. Skip. Yeah. Okay. So next question is John has a bag of 8 color tokens, of which 1 is blue, 2 are yellow, and 5 are red. The blue token is number 1, the yellow token is number 2, and then the red tokens are then number 1 to 5. So the tokens are only distinguishable by color and number. So part 1. Find the number of ways in which the tokens can be arranged in a row if the tokens are in ascending order. Part 2. John picks 3 tokens from the bag and arranges them in a row. Given that the sum of the tokens is 10, and the tokens are not all the same color, find the number of possible arrangements. In part C, find the number of ways in which the tokens can be arranged in a circle such that no tokens are numbered 1 and are placed to each other. So part 1 first. If they want the numbers to be in ascending order, we just consider arranging all the number 1s first, then the number 2s, and then the number 3s. So in this case, we have 3 number 1s, so 3 factorial 6. Then we have 2 number 2s, so that is 2. Then the thing is that for 3 to 5, we only have 1 red 3, 1 red 4, and 1 red 5. So in this case, it's just one scenario, so the total number of ways is just 6 times 2 times 1 is 12. And part 2, they just want to see if the sum of tokens is going to be 10. So in this case, there are 3 different scenarios. You have a red number 5, a red number 4, and a blue number 1. And you have a red number 5, a red number 4, or a yellow number 4. Or you have a red 5 and a yellow 2. And a red 3, yeah. So you have these 3 scenarios, then you just times for each of them the 3 factorial. So first case will be 3 factorial, second case 3 factorial, third case 3 factorial also, because we're just arranging these unique balls. So as a result, it's just 18. And so in this case, counting the difference can work. And the last part, find a number of ways in which the tokens can be arranged in a circle, such that no tokens are number 1 are placed next to each other. So in this case, we just exclude all the ones. So there will be 6 other numbers. And then in this case, we just, since 1 factorial, arrange those non-number 1 tokens. Then there are 5 gaps. We find a way among the 5 gaps to choose 3 spots that will have the number 1. Then afterwards, 3 factorial, because we can replace those colored ones between their positions. So in like a specific scenario, we can then arrange these ones within themselves, which is why you have the 3 factorial. And so there will be 1440 ways. Then this is another question. Alyssa and Bruce won a hamper at the competition. The hamper consists of 9 items. How many ways can 9 items be divided? If each of the has 1 item each, or part 2. How many ways can 3 more items be selected? Count 9 items. So for the part 1, the possibility, let's say without restriction, is 2 power 9. But then we can consider the scenario where Alyssa gets nothing and Bruce gets nothing. So actually the answer is just 512 minus 1 minus 1. So in this question there are 3 different scenarios. Alice gets an item, Bruce gets an item, or the other scenario is they get nothing. So in this case it's just gonna be 512 minus 1 minus 1. And how Alyssa can get nothing is if Bruce gets everything, or how Bruce gets something is if Alyssa gets nothing. Then vice versa. Then for part 2, how many ways can a set of 3 more items be selected from 9 items? So it's similar to the first part. You take 2 power 9, but then you minus the scenario where 0 items are chosen, minus the scenario where only 1 item is chosen, then you minus the scenario where only 2 of the items are chosen. Then you get 466. So there are 3 solution points I have. Is that a permutation will be an exact arrangement, but then a combination is just choosing what numbers or like what set you want. It doesn't consider exactly where it's specifically arranged. A combination just wants things without any particular arrangement, like grabbing into a random bag of candy and just taking everything out. You don't order and count which is the first candy you got. Then for circular permutations. Why we use n minus 1 factorial is because we are fixing one person as a reference, and then we arrange the people or objects around him. Then counting is a valid method, but usually use this as a last resort and when the answer is less than 30 or around there. So there are about 4 basic strategies that you can use for arranging objects. Now will be fixing positions. So you fix one object first and you arrange around it. Second is must be together. So in this case, you group the things together and tie whatever you need to find as one unit. Must be separated. It then means sorting method. You arrange the other stuff first, and then this will create barriers, which we can then slot in the remaining stuff to make sure they are separated. Then the complementary method, which is if the direct method is too tedious, it is more efficient to count by taking all the possibilities minus a complementary set of for like at least or at most questions, which basically means we are looking at the extreme example and we're taking all possibilities minus this extreme example to get the remaining we want. That's what complementary method is. Then for unique questions, there is the case of duplicate vectors. So remember to divide by 2 factorial or whatever after writing all the 5 choose 2, 9 choose 6 or whatever. So if they say that there's at least 1 from each group, find the case where there's no A, no B, no C. So this is basically complementary method. You take out the extreme scenarios. Then how many ways can a set of 3 more items be selected from 9 items? You can just take the one cases where nobody gets anything. The number of way 1 item is selected, and the scenario where 2 items are selected. And so with that, that's all I have for P&C. Hopefully this helped you gain a better understanding and hope to see you in the next video. Bye!